Next, we have a couple of lightning talks. These are short 5-minute talks by speakers who have topics of interest that we've chosen. And our first talk today is going to be Dr. Bill Samuels. He was the guest speaker on our first seminar of this series, and he told us then about the icy water application for modeling contaminant transport. And with the news, the big spill in Colorado in the news the last month or so, we asked Bill to give us a quick update on how that application's been used in response to that incident. And so, Bill, could you just briefly reintroduce yourself and go ahead with your presentation?
Well, thank you, Al. Yes, I'm Bill Samuels. I'm with Leidos Center for Water Science and Engineering in Alexandria, Virginia. And we have developed a toxic spill modeling tool under contract with the Defense Threat Reduction Agency. It's called Icy Water. And I'm going to show you how it was used to do some forecasting of the downstream transport of the Gold King mine spill. This spill event occurred in early August of 2015. It was a result of an EPA investigation into the mine to relieve the mine of the water that had been accumulating there for some period of time. And as a result of the excavation of the mine, the entry point had collapsed, and a large pulse of contaminated metal-rich mine wastewater spilled into the North Fork of the Cement Creek, which is a tributary to the Animas River. And it was a very quick release, about 3 million gallons of water spilled in about 1 hour. The graphics on this slide show an overview map of the location of the Gold King mine. It's in the vicinity of many other abandoned mines in this region. And then on the right-hand side, a zoom in on this area, showing the location on the North Fork of the Cement Creek and some of the downstream tributaries. One of the first things we did was an icy water, what we call a quick trace, which is just a time of travel calculation. We went downstream 48 hours. And you can see then we color-coded this downstream trace by 4 different time intervals over that 48-hour period. The graphic on the left shows the hydrograph from a gauge on Cement Creek near Silverton, Colorado. You can see the pulse of the spill clearly shows up in that particular gauge on August 5th. We did some comparisons between the modeling results and some observations that were reported. This was a report that was published in the Denver Post on the time of travel of the spill at a number of different locations downstream. We superimposed those locations on the icy water map and compared the forecast time of arrival with the observations. You can see the graphic or the table there in the middle of this graphic. Fairly good agreement between observations and forecasts. We were off. We were a little bit slow initially in predicting the time of arrival, but as it moved downstream, the results seemed to converge a little bit better with the observations. Another analysis that we did was to forecast the time of arrival at Lake Powell. This was an 8-day travel time period. There were about 10 USGS real-time gauges reporting flow in this path, so it's about 400 miles downstream from the spill site to the confluence with Lake Powell. And then as sampling was done and measurements were being made of various metals by EPA, that data was being made available to us as well as many others. we did some initial comparisons between manganese levels that were observed. You can see that in the upper graph there. There are actually a number of different metals that are being reported there. Our model predicted a peak concentration of manganese of about a little over 7 milligrams per liter. What was observed at this location, which was on the Animas River just below Silverton, was about 6.65 milligrams per liter, so fairly close agreement. There was some disagreement in the peak time of arrival between the model and what was observed. So we're looking into improving some of the flow-velocity relationships in icy water. And so just a quick summary of what was done. We used the quick trace tool to compute initial time of travel. As mentioned before, it was about an 8-day travel time to Lake Powell. There are hundreds of abandoned mines in the vicinity of this particular mine. And some of the improvements that we'll be looking at is the flow-velocity relationships in icy water. And just a quick comparison between this spill and the one that occurred in West Virginia back in January of 2014. The Elk River spill was 10,000 gallons of an organic solvent. This was 3 million gallons of acidic metal-rich mine wastewater. Elk River was a tank leak. Gold King Mine was a mine breach. The major effect on the Elk River was the contamination of a major water supply, the city of Charleston, West Virginia. For Gold King, it was effects on drinking water availability on several municipalities downstream, as well as effects on irrigation and the use of the river for recreation. And in our tracing for Elk River, we were looking at about a 250-mile downstream trace, and here we looked at about 400 miles of river in terms of downstream traces. So that concludes my presentation, and I thank you for allowing me to show these results.
Great. Thanks a lot, Bill. That was very interesting. Nice to get an update on icy water and see how that's working. Our next lightning presentation is by Elizabeth Zeiler, and I'll let her introduce herself. She's going to talk about making the case for integrating 3DEP and NHD. So, Elizabeth, can you share your screen and go ahead with your presentation?
Good morning. My name is Liz Zeiler, and I am the NHD steward for New Mexico. And today I'm going to talk to you about the need to integrate two USGS products, the National Elevation Dataset and NHD data. As mentioned by Jeff Simley in his 2013 concept paper, this is somewhat of a chicken or egg problem. Historically, hydrologic data was mapped by cartographers first, and then with the advent of new technologies, and especially LIDAR, we find that this new data set can help us to use the elevation data set the LIDAR data set to inform the NHD. This image shows our project area here. We have a stippled area in this rectangular area. This is Santa Fe County, and down here, this area. The purple areas are quality level 2 data, or do not represent quality level 2 data, nor are they publicly available data. The hashed areas here and here are data that will be processed in 2016. So you can see that we're a long ways from completing the LIDAR processing in New Mexico. The project area covers some 3,000 square miles. It includes Santa Fe County, and the LIDAR was collected and based on a nominal pulse spacing every 0.7 of a meter. This results in a 1-meter DEM. The image on the right shows the same surface reconditioned to reflect surface water flow. In this example here, there are over 180,000 vectors modeled from this associate DEM. Clearly, we need to determine how to efficiently get at the value of the data. When you look at the branch complexity here on the right, stream orders range from 1 to 10. And clearly not all of these streams are modeled with precipitation or soil moisture in mind. 3/4 and 1/4 of the streams are classed as 3s or greater. This presents a conundrum of sorts. In this example, the DEM was reconditioned, and you can clearly see that the channel flows accurately down this culvert here. The NHD data flows outside of the channel here. And here we see some more discrepancies in the data. The reconditioned surface flows properly down this channel. However, when you get to this point here, it appears that the reconditioned surface may not be routed correctly, and perhaps this barrier needs to be removed. If we were to use the NHD data set for modeling, it might result in lives and property being damaged. So this is somewhat of a conundrum. We have this very accurate elevation data set that we can use to improve the NHD, and here you can see that the geometries align here. But over here, it's not so obvious where the alignment occurs. And over here we have a different issue. Here we have the reconditioned surface that flows outside of this levee. However, the NHD looks like it runs properly down the channel and actually is perpendicular to the levee. A similar problem occurs here, where the reconditioned surface goes around the levee, and we actually need to remove this barrier here so that the channel flow is proper. In closing, I'd like to say that there is a need to integrate the 3D elevation data set and the National Hydrologic Dataset, that we should make use of the more accurate elevation data, and that we've seen an expressed need from the hydrology community for this data as reflected in the HRBS study, which is the Hydrologic Requirements and Benefits study, as well as the LIDAR requirement study. And we need more research and better tools to integrate the two data sets. Last of all, I'd like to thank my two partners, Santa Fe County and Bohannon Houston. Thanks.
Okay, great. Thanks, Liz. That's a very interesting presentation. So that will conclude our presentations for today. Appreciate everyone's participation and attendance today at our seminar. Thank you.